Hi there. In this video we'll learn about shear flow and how to analyze shear in general in thin-walled sections. What we learned so far is tau, shear stress in beams, is equal to VQ over IT. In rectangular simple cross-section, you will find that at the top of the beam, the tau is equal to 0. And then the more you go in depth in the beam, the more Q will have. So on the top of the beam, slicing the air results in Q is equal to 0. And then the more you slice of the beam and increasing that depth here, that increases the area and the first moment of inertia of it around the centroid, the neutral axis here. And that increases Q, so tau here increases parabolically. Non-linearly here, until the maximum value we learned happens at where Q max happens, which is any point along the centroid will have tau max. So that's what we learned so far. The other thing we learned is the shear stress in wide flange sections. So we learned that when we do that slice A prime and the other slice C prime, the CC prime slice, I know that it's at the centroid of the section, and this is where I expect to have Q max and tau max. And then when we slice through the flange, we say that we are now slicing over a wide slice here, or are we taking a lot, cutting through here a lot of material of that section. So T here, if you look at the formula VQ over IT, T is so big when you slice through the flange, but small when you slice through the web. So that gives us this distribution of shear stresses in a wide flange. So kind of most of the stresses are in the web part of the section, and very little stresses develop in the flange, the way we slice here, because we are kind of slicing over this whole width of the flange. So that's one thing, is that the flange are not active in like carrying the shear, but is this that's not really the case. We'll see that. Also, another thing is the theory that we are considering is that the formula here is VQ over IT, and Q is calculated for any point at a y distance or coordinate. So Q is constant at any y value, or all the points that have the same y value, which means that tau is constant for all the points that have the same y value. So this is the theory. Now in reality, this is not the case. So in experimental studies, they kind of analyze in different lab methods, the stress distribution, the shear stress distribution in sections. And the idea here, they started analyzing this distribution. If you look here, there's always, it's not a uniform, so you cannot say it's the same tau over all the points along the same y coordinate. So there will be variation here, and we're looking at tau max. We were looking at tau max here and how it relates to tau average, which we calculate using VQ over IT. So this VQ over IT is what we refer to as tau average, and tau max is what they found experimentally the maximum shear stress to be. And they started changing that ratio between the width of the section and the height of the section. And you can see here for slim sections, meaning that B is small and the height is large, like in the web part of the section, the ratio here is close to 1. So that's correct here, that's pretty close here. But once you go into kind of a square section, you start seeing a difference. But then once B becomes larger than the H here, so kind of it's more like a shallow section, so it's more like flat, not deep. The values, or the ratio between tau max, the actual maximum stress that develops, shear stress that develops, and the average that we calculate using VQ over IT becomes really big. So there is a big difference here. The more you have that ratio of B over H, the more difference in error actually. That's a big error here. So the idea now that we get is that formula here is not valid when you start analyzing shear stress developing in non-cylinder sections, or the way we cut the section results in that B or T part. T is too large considered to the depth of that part of the section or the whole section here. So the idea is here we need to revisit when we're dealing with thin-walled sections like wide-flange or circular or rectangular. Anything that has the walls here are kind of considered thin relative to the bigger dimension or overall dimension of the section. We need to really think carefully here about how shear stress develops in these sections. So let's go to my whiteboard here to explain that in details. So we have here, this is a wide flange subject to a shear V, and we are interested in calculating the shear stress that happens at point A. So what we used to do up to this point is you slice, the beam like this. So you slice over the whole width of the flange, and that will develop shear stresses transverse and longitudinal, like we see here. And if we put coordinates, so these stresses will be tau xy, tau yx. And because T here is so large, like we've seen in the distribution of stresses in the slides, the stresses in the flange here are small compared to the stresses developing in the width, because T here is too large. Another thing here is we think about the flange here as its own section or its own part. So the skin of the flange at the top will have zero stress. The skin of the flange at the bottom will have zero stress, because if you start slicing locally, like, you will not slice that much, so the Q here is equal to 0 at the top and the bottom of the flange section itself, or if we focus or zoom on the flange only. So imagine 0 and 0, and the values already are small when you start slicing through the middle of the flange. So we say that the way we slice here and the way we analyze shear stresses will result in almost zero stresses in flanges. Besides that, the theory is not correct, because you're slicing over a long width here, and we've seen that the ratio between the actual maximum stresses and the theoretical stresses VQ over IT is too big, and there's a lot of error here that we're dealing with. So what's the case here? Should we say that we ignore the shear stresses in flanges? That can be said, yes. Some actually, engineers, practitioners assume that the whole shear is just carried by the whip. But in thin-walled sections, local failure can happen because of shear in flanges. So we have to be careful about that. So the idea is we need to analyze shear in flanges in a little different way. So instead of slicing horizontally like we have seen in the first case, now for the same point, let's think about slicing vertically. So perpendicular to the length of the flange, instead of just horizontal, which is typically what we used to do, because we always slice perpendicular to the direction of the shear. But now let's slice perpendicular to the direction of that thin wall of the section. So in this case, it's perpendicular to the flange. And if we zoom in into that part, and we learned in driving the tau equal to VQ over IT, that was a couple of lessons ago, that because of the difference or differential delta between the normal stresses, so now connecting shear with normal stresses, what's happening here? But if you go back to the previous lessons, the way we derive VQ over IT is by looking at there is a difference in moment values between little distance of the beam along its length, so M and then M plus delta from the other side. So that results in differences in normal stresses between the front and the back faces of that segment of the flange. And this, using the same concept, so go back to the lecture that explains the tau VQ over IT formula. Using the same process, we will derive that to have stability and equilibrium here, there should be longitudinal shear developing in that part. So it's kind of longitudinally in that segment, that purple part of this flange segment. So if it's longitudinal from equilibrium, from the general state of stresses, there should be transverse shear. But now it's actually not developing kind of transverse vertically. It's actually transverse along the length of that flange. So it's kind of the longitudinal shear here. The transverse shear here is developing parallel to the boundaries of that thin-walled part of the section. So it's parallel to, in this case, it's parallel to the boundaries of the flange. It's not going from top to bottom. It's going from right to left. So not to be confusing tau that we used to be like VQ over IT, and it's in other section, not the thin-walled sections. So in thin-walled section, we refer to the shearing action in general using shear flow. So Q lowercase, and we'll use shear flow to study. And shear flow here is really meaning, like it has a meaning here because it's actually we are representing shear as it behaves here. Shear flows through the section itself, and that will help us to figure out the direction of the shear and the magnitude of the shear in thin-walled sections. So there are some rules here when we start analyzing shear flow, and we'll go through these 6 rules in that wide flange example in details. So let's say this is a wide flange. It's kind of making a little the thickness of the section here a little big, just to be able to draw things over it. So if we look at the first and the second rule, so Q flows through the section, and Q flows parallel to the boundaries of the section. So flowing here means literally, if we represent the section now as kind of like water channels. So the Q here, that transverse shear, the direction of it is kind of flowing through the walls of that section. So I know first of all that the edges of the section I have 0 shear stress because I'm slicing through nothing, right? So Q is equal to 0, so Q uppercase is equal to 0, so Q lowercase will be equal to 0. Now, following that, now the center line of that wall of the section or walls of the section, that will be the path of the transverse shear flowing through the section. So that's kind of the first and second rule, is first that flowing concept. And it's flowing parallel to the boundaries of the section or the boundaries of the wall, forming up the sections here. So one thing I know also is that on the neutral axis, the Q lowercase and tau are maximum values. So I know that there is a maximum value in the middle of the section. I know there are 0 Q values at the tips of the section. And Q follows the same direction as V, so you're starting from the 0 ends or 0 values at the top, and you start flowing. And the idea here is flow and increasing the value here because you're cutting through more meat or slicing more meat. More meat means more tendency that that part will slide and shear with the other part of the section longitudinally. So the shear here will keep increasing from 0 slowly, and then kind of joining forces until maximum shear stress and shear flow at the centroid of the section, neutral axis, and then start diminishes and decreases up to it reaches 0 at the other lower tips of the section. So that's the meaning here of flowing. You start from 0, at some point of the section, you flow through the walls of the section, you get the maximum at the neutral axis, and you start kind of disappearing up to 0 at the other ends of the section. So that's the first and the second rule. The 6th rule here is that cuts are perpendicular to the segments of the wall. So just it's not always horizontal. It has to be perpendicular to the wall that you are analyzing the shear stress at. So for flanges, the cut will be perpendicular to it, so it will be vertical cuts. For web, it will be horizontal cuts. For rule 5 now, Q refers to the area from the points calculate tau or Q lowercase to the point where tau is equal to 0 or Q is equal to 0. So for that specific cut here, I'm analyzing the area from that cut, from that point, all the way to the nearest point where it has 0 shear, or to the nearest tip, you can say. So to look for from this point to the nearest point that has Q equal to 0, and that will be the area that you will analyze in terms of calculating Q uppercase for it. The next rule is Q varies linearly in segments perpendicular to V direction. So if my V is vertical, and let's say now I QF here, that first Q that I calculate for the first point in the flange, and then kind of progressing a little to the left, I calculated QF2. So now I have kind of this yellowish kind of small segment, and then when I switched a little to the left, now I'm cutting bigger part of the flange, which is Q, which will give us QF2. Now if you look at both of these segments or sections or points where I have QF1 and QF2, they both have the same Y bar, because Q is equal to what? It's equal to the area of that shaded part that is kind of sliced at this point times the centroid of that area. So when you move horizontally and the shear flow is vertical, so you're referencing to the centroid of the section, Y bar for both QF1 and QF2 is the same, and the only thing different is just the area, and the area increases here linearly because you're just extending the width of that QF or A psi here. You're just extending the length a little, and that's a linear change. And that means that if Q uppercase changes linearly, everything else in the shear flow formula, VQ over I, is fixed. V is fixed, I is fixed. So Q changes linearly. This means that Q uppercase changes linearly, shear flow changes linearly also. So the last rule here is related the same way, but if you're dealing now with cuts or parts of the section that are parallel to the V direction, like the width, in that case Q varies or changes parabolically, because both, if you look at the Q formula, is equal to A times Y bar. When you move vertically and change your points vertically in the section, your area psi here is changing, and the centroid location of that area, or that the part that you slice, also changes. So that's kind of double change. That's not linear change. It's parabolically. So if we look now at the section, this means that the distribution of stresses, these triangles here, is just a distribution of graphing distribution of shear flow over the segments, the flange. And you see it starts at 0 and keeps increasing up to that right flange meets with the web, and the same thing for the left top flange until it meets the web. Same thing for the right and left parts of the lower flange. So all of these will end up with a QF value here. And you see it's a linear change. For the web, you start at a value roughly equal to 2QF. So remember, it's kind of a flow, right? So you have a shear flow coming from the left part of the flange QF, the right part of the flange you have QF. They join forces, and they result in kind of together into a new Q at the top of the web. But the thing we're missing here is that little block here, that kind of brownish, crossed part. That was not accounted for QF from the right or the left. So will be the little difference. But when you calculate this point that has 2QF value, now you're slicing perpendicular to the web, right? So you slice now horizontally. And now your Q uppercase, the first moment of area now is for the whole flange, which is kind of addition of the Q that you analyze for the right tip or the flange and the left tip or the flange of the flange. So this is why kind of the flow when they meet from the left and the right part of the flange, when they meet, they add up together to a larger value, which is here roughly is equal to 2QF. And I know that this 2QF is not the maximum Q, it's the maximum Q, maximum shear flow is at the centroid of the section, so they will increase to Q max, and it's not a linear increase, it's parabolic increase like we have seen here. So that's basically application of the shear flow rules and how to draw them. How to calculate them is just the same formula we covered discussed before, VQ over I. There's no T here like the tau formula, but it's very important to know the direction. Where is the direction of the shear acting that's really acting and affecting that part or that point in a section, in a thin walled section. So you have, remember, it's Q flows and it flows parallel to the boundaries of that thin walled part of the section. You have to do cuts for analyzing the shear stress and calculating Q uppercase perpendicular to the walls of the section, or that part where the the walls of that section at this point. You calculate Q from this point up to the closest point that has Q is equal to 0, or shear flow equal to 0. And we conceptually now understand that shear flow changes linearly in segments of the section that are perpendicular to the shear force, and the shear flow changes parabolically when you have when you are dealing with members that are parallel to the shear force or the shear direction here, V. All right, so in class we'll see more examples of thin-walled sections, and we'll apply these rules and try to visualize and graph here the shear flow direction and expected magnitude and values for of it. So hold tight until we do that in class, but this is kind of an intro into shear flow and how to draw them and how to use them now to really understand the shear behavior in thin-walled sections. Thanks for watching, and take care.